Um, so
Yeah.
multiply the molarity by.
That's the rest of everything I need to hand in.
Sweet.
Sorry I flooded your inbox.
Oh, no, you're fine.
And then you multiply the moles by the mole mass. I've got great what's it called? Visual memory.
Ooh, nice. I do not.
Does not help though. You remember the answer, you're like, I know the answer. This is the one we did last class.
Yeah. Yeah, try to at least read that.
You said all math, right? How did you?
Sorry, pass that to me.
This one? Oh. Yeah. Yeah, I think I was gonna do the calculus one next. I think I had a class too. Sure, it's chemistry and physics. It's not as comparison. Not as good.
let's go ahead and get started. So I was trying to pass back quiz 8 for y'all. So I have one quiz though with no name. So if you checked your grade in the grade book and you turned it in physically, but you don't have a grade, check in. And it's someone with pretty nice handwriting, but I can't think of who it could be yet. All right, so let's, So let's just start off with kind of our review. And so we'll be in a similar format to last time, right? We'll have our first part, that's multiple choice. Right now, I think it stands at around 30 questions. And so I think I'll probably leave it at 30 because I did 34 last time, but I think these are a little more math heavy. So I'm worried they'll take you longer. And then I'm still kind of tweaking the second part, which again will be free response. And just like before, the multiple choice portion will be closed book. And you are allowed, though, write your periodic table. And so you could write formulas on your periodic table, but just basically write one kind of cheat sheet. And then the second part will be free response and, again, open book like last time. So you can have open, notes and everything. Obviously, just no Google or ch221 or anything like that. And so let's just start off with a problem. So this is from your quiz, and I brought it up because it may make a reappearance on your multiple choice question. And I let it slide on your quiz, so I gave most people the credit. And we can just go over this one. And this was a C1V1 equals C2V2 calculation. And so then most people did write the work, so we can just set it up together. So we have 10 milliliters and 6 molar solution. We're trying to figure out, right, our V2 to make a 1.5 molar. And then most people, right, they did their calculator, and punch this in, so times 6, right, divided by 1.5, and so you got 40, and so most people circled 40, except what did the question say? So it said how much water must be added to 10 mils, right? So it's saying you have 10 mils and then you're going to add water to it, right, to give it to a final volume. So I accepted most people's answers, I believe, for 40. So I let that slide again for your quiz, but for your exam, I may not be so lenient, right? So you had to add 30 milliliters because this was our final volume, but we already had 10. So this was the true correct answer. So that's what I'll be looking for again on the final, hint, hint, if this question makes an appearance. And so question in the chat, the exam is just mainly focused on the second half, but of course chemistry is cumulative by nature. All right, so let's go over other types of maybe shorter multiple choice type questions. And so if you go on to Blackboard, though, I did add a little something for y'all. So it should be under, and I apologize, with the new Blackboard, the whole content shell thing got all messed up, so now it doesn't make any sense. I apologize, but underneath week 10, I have just a little extra spot over here, practice problems. So you can do a few more quiz type review problems, and hopefully you can do them over and over again. I'll double check the settings on the assignment. If not, just email me. That's available for you to practice. And then, of course, under week 10, that's where I hid the study guide. So that's not too helpful in my opinion. It just kind of lists the overview of the terms, but still might be useful. So just a quick reminder of what we're covering. And I would just focus on the chapters. So I'm not going to ask you like inter-chapter trivia or anything like that. So yeah, not into all this trivia. So just focus on the chapters. All right, so let's look at other types of questions. And so we could have a multiple choice type question that asks, there's really one of two that we could have, or maybe both. So you'll see this. So what sample has the greatest number of molecules? And so is it 5 grams of helium, 5 grams of argon, 5 grams of krypton, or 5 grams of xenon? And so while you're thinking about that one, I'll write the other style of question. So what's the trick with these two questions? Because you want to answer this one quickly on the exam. So let's look at the first one. So it says, again, what sample has the greatest number of molecules? We're given different amounts in grams. Well, they're all the same amount, different atoms. So what's the key for this one? Yeah, so smallest atomic weight. And so this one I just so happened to just pick a bunch of single gases, but right, just don't get tripped up if it's like methane versus, ammonia. So obviously you're going to have to compare the masses. And so good, so pick smallest molecular weight. So again, whatever the case is. And of course, for these answer choices, right, helium is the smallest, so greatest number of molecules. And then what's the deal with this one? So they're the same, right? So that might try to trick you up on a, again, multiple choice questions. Of course, these are now all moles. So now, of course, all the same number of moles. All right, let's, oops. Oh, that's fine. Sorry, I have too many tabs. That's not the right class. All right, let's do a limiting reagent practice. And if you have other questions, topics, you can, again, post them in the chat or ask. And so we'll practice with our good old Haber-Bosch reaction. And so it's balanced. And so now let's ask, so when 25 moles of H2 react with 12.5 moles of nitrogen, what is the limiting reagent? So how would we do that one?
You have to find the atomic mass of each molecule first for the formula.
So we'll let people think about that. So what are we thinking for this one? What do we have to do? Yeah.
You can express it as a ratio. 25 to 125 is the same spot to 1. So you compare it to the formula here. You have 3 to 1. So nitrogen has to be, or hydrogen has to be the right end.
So, yeah, what you said was correct, just maybe a little fast. So you made this point of a 1-to-3 ratio, so you can multiply nitrogen times 3 and see that you have a lot less hydrogen. And so that would work. I'd probably just personally set up a relationship looking at ammonia so we can tell. So if we do that with H2, so we have 25 moles of hydrogen, and then again comparing our balanced equation, so hydrogen on bottom to ammonia on top. Oops. So 25 times 2 divided by 3. So that gives me about 16 moles of ammonia, 16.6. And then repeat that with nitrogen. So then we said, okay, 12.5 moles of nitrogen. and now they're a 1:2 ratio. So that gives me 25 moles, so reaching the same conclusion that H2 was the limiting reagent. So other questions on that one or methods? No questions on this one? Let's do another. We'll do another little stoichiometry one. So we'll try. So we can measure iron by precipitating out iron sulfide. I want to know how much iron nitrate, I should say iron 2 nitrate, was in my original sample if I reacted iron 2 nitrate with excess sodium sulfide to produce 12.34 grams of iron 2 sulfide.
The 2 on iron 2 nitrate indicates the charger.
Sorry?
Does the 2 on the iron, is that charge or is that the number of valence electrons?
So remember, it's oxidation state.
Yeah.
So how's this problem coming along? Before you start doing calculations, what might you want to just write out first? So then, what's the formula for iron nitrate?
FeNO3 2.
Thank you. So FeNO3 plus, and then what's sodium sulfide's formula?
Na2S.
Na2S. Looks good. And so then it said we're going to produce iron sulfide. So, right, looks like a double displacement reaction. So we'll get iron sulfide and then 2 equivalents of sodium nitrate. All right, so that looks good. And so now what's our next step? We have our equation. They told us we have 12.34 grams of iron sulfide. We want to know iron nitrate. So where do we go from here? Yeah.
You can find the formula mass of iron 2 sulfide.
Yeah, so let's do that. So does anyone have that molecular weight handy? So 87.911. So I have about 88 in my notes. That looks good. All right, so let's find moles then. So 12.34 grams of our iron sulfide. So let's find moles of it. All right. And then what do we want to compare it to? What mole-mole ratio? And then where do we go from here? Yeah.
You can use the ingredients in that as it is on the reactants to figure out how many moles of each one you need.
So perfect, right? And this one's nice and easy. And, you know, it's nice to write out your balanced equation, even though this one's a nice 1-to-1 ratio, but just helps you to see that. So now we can say, okay, for every 1 mole of iron sulfide, that corresponds to 1 mole of iron nitrate. And then what's our last step if it's asking for prime mass? What's our last molecular weight that we need, really?
That would be the iron nitrate, right?
Yep, so right now we got to add up our molecular weight of iron nitrate. What do people get for that one? Watching the chat too.
I got around
159. Double check that. I have like 179-ish in my notes, but
I have 179.853.
so that's closer to what I have. 179.85. Is that what other people got?
Yeah.
Okay, good. Just double check all the little addition there. Make sure you do, right, 6 oxygens and 2 nitrogens. You could also think about adding the nitrate first and then multiplying that by 2, whatever's easier mathematically. And then, of course, on an exam, right, show your work. I would even show it on the multiple choice questions just in case, you know, you add up something wrong. I can at least trace back what happened. And so then we'll do that, plug that in. So grams per mole. And so now let's just punch everything in. So I'll just go through kind of step by step. All right, so we're getting about 0.14 moles of our iron sulfide, 1-to-1 ratio, and then multiplying by our molecular weight, 853 or so. And so then I get a final mass of 25.5, if we round, grams of our iron nitrate originally. Right, that sound okay? So let's shift gears for a second. We'll try another type of problem. So let's practice. And so we want to know, so what is the overall energy for this process? Of course, we want to determine, is it exothermic or endothermic? And so it looks like we're going to be taking ethylene here. Let's see, double bond. And then this is called a bromination reaction. So once you go on to organic chemistry, you'll learn all about these. And so you can brominate across the double bond using bromine, actually, wonderful reagent. We've discussed how it's liquid. So that's why it's useful for our organic chemists. So now we're doing that. And let me give you some bond energies that will be helpful. So given the following, so a C, double bond C, is worth 611 kilojoules per mole. A single bond is worth 348 kilojoules per mole. A bromine single bond is worth 193 kilojoules per mole. And a carbon bromine bond is 276 kilojoules per mole. So go through that. How would you determine this?
We need a hydrogen's energy.
I think you have all the bonds you need.
When that double bond, like in the, I don't know, it's just kind of like when that CC double bond breaks, does it just like transfer to one bond, or does it break and then re-transfer to single bond?
Just do it like with the energetics. So yeah, like where we break it fully and then, yeah. Because in reality, you're right, like it just goes to a single bond and makes this like transition state, but that's not what we're calculating here, yeah. Yeah, we're just doing the mathematical. how is this problem coming? Are we just working through it? Do we know what to do? Oops.
You just add the bonds that are created and take away the ones that are taken away.
So add the bonds that are created, but what sign is it when they're created?
I guess it'd be negative, right?
Yeah. So just making sure we're all on the same page. So yeah, we'll take our bonds formed, so they're going to be negative, so getting energy back, and then tallying up our bonds broken, so putting energy in. So let's go through that together. So what did you find that you had to break for this one? So our carbon double bond, so that was 611 kilojoules, and there was just one of those, right? Then what else do we have to break?
The bromine single bond.
So our bromine single bond, and again, just one of those, so plus 193. So it looks like we put about 804 kilojoules in. So you can check my math on that. And then, so let's see what we got back out. And so what was formed? So one carbon single bond, so 348. And then you said 2 carbon bromine bonds. So that's 276 times 2. I'll pull out my calculator for that one. And then, of course, this is negative, right? So negative 900 versus positive 804. So now we can add those two together. So watch my signs in the calculator. And then we should end up with a complete change in enthalpy of negative 96 kilojoules for this process. And then we can say that it was exothermic as well. Questions on that one? Yeah.
Why is it exothermic if it ends up with less energy than it's releasing?
Because remember, exothermic, it's releasing heat.
Oh, okay.
Yeah, so reactants are higher in energy than the products. So yeah, it had to release heat. And then obviously, right, we'd be feeling that though as positive 96 kilojoules of energy, right, coming into us being the surroundings. So.
Is there a term for endo-exothermic for light when the atoms releasing or absorbing?
I mean, just like emission or absorption. Let's see. Let's do some of these other enthalpy ones. And so we're looking at another standard enthalpy of formation where we can take 2 atoms of carbon plus 1 equivalent of hydrogen gas to give us C2H2. And so, of course, we want to figure out the change in enthalpy for this. And so we are given the following. And so we have C2H2 plus 5/2 oxygen gives us 2 equivalents of CO2 and water. And that is negative 1299.5 kilojoules for that process. Then we have our combustion of CO2, our standard enthalpy. So that is given, negative 393.5 kilojoules. And then the last equation that will be helpful is H2 plus half an equivalent of oxygen gives us water, and change in enthalpy, negative 285.8 kilojoules. So I'll let you think about that for a few minutes. How can you arrange these, right, to give us our enthalpy for C2H2? So what are we thinking for this one? Have we managed to add them up yet to give us our desired enthalpy. What if we just look at this one? What do you notice about that one? Yeah.
You can sort of decompose the, the formula into the bottom two. You can take each element, add it up, and then put it in parentheses. And so long as you have the proper left side formula for the bottom two, you can use that to figure out the sort of the heat coefficients or numbers that go along with it. And you just use the number of each formula to get the total.
So then, yeah, so kind of walk us through that process. So did you do anything to the first equation?
Yeah, that was a C plus O2, and that creates CO2. And on the right side of the equation, it creates 2 CO2 and 2 H2O on the top equation. But the 2 CO2 there is important because that shows that you need 2 of the carbon and O2 reactions. And so you can put a 2 and then the left side of the equation in parentheses.
So you want to double this second one?
Yeah. And then you need the H2O as well, which is on the right side of the bottom equation. And so, because you have the heat there, and you only need one water molecule, you can do one of those. And then it's just the total heat times 2 of the first equation times that of the second.
And then we still need to flip the first equation though, right? Because that will balance. So you're saying the right things here. And so other hints why we know to double this is, right, we have 2 carbons, and then we don't really have anywhere else to get carbons from, right? So that's our other hint to balance that. I know you saw the CO2s, right? But that will help us later, those 2 CO2s. And I get what you're saying, but right, to get them to cancel, because remember, we have to add up the reactants and the products and then cancel out what's the same on the reactants and products. So we will need to flip the first one. And so the other hint that we have to flip this first equation is, right, that the C2H2 is currently on the reactant side as shown here, right? There's no other sources of C2H2, but we need it on the product side. And then, so let me do that, and then you might have to remind me what you said for the hydrogen, if that just added in there. So let's just start rewriting that. So I'm going to flip the top one to 2 CO2 plus our water. Gives us our oxygens plus acetylene. And so again, don't forget to flip the sign, so I'll do that now. So 1299.5 kilojoules. So multiply the second one times 2. So 2 carbons plus 2 O2s give me 2 CO2s. So there goes the CO2s canceling like we were desiring, right? So that looks good. And then, what did you say for the hydrogen? Did you just say to add that in there?
I saw that there was a water equation there that would match with the equation there.
So yeah, that does match with our flipped. So that's one hint, right? You have the water here. We need it to cancel. Again, I was kind of looking more simply at just where do we have hydrogens, and that was only in this equation. So let's just go ahead and add this in there, right, without doubling or anything. So H2 plus our half O2 gives us water. And so now we need to kind of see where we're at. So right, we mentioned that water was going to cancel. Okay, that looks good. And then check where we're at with the oxygen. So we have 2 plus a half, right? So that's 2.5. which is the same as 5/2. So that looks good, right? So all that oxygen mess ended up canceling. And so it looks like we are left with our desired equation, right? So 2 carbons plus our equivalent of H2 gas gives us acetylene. And so now we just have to account for what we did. So this is still negative, right? Our enthalpy, we just have to multiply the second equation times 2, and then add in the enthalpy of our last one there, so we didn't do anything to the hydrogen one. So let's see where we're at. So 1299.5 plus negative 393.5 times 2 plus negative 285.8. And so I'm seeing 226.7 kilojoules in the chat as well. Is that what we got in here? I see some nods. So then now we can say the change in enthalpy, or our standard enthalpy of formation of acetylene was 226.7 kilojoules. I'll put my positive sign there again just to really emphasize that that was endothermic. Questions on that one? Definitely we'll see something like that on the exam.
Are we going to see resonance forms and formal parties on the exam?
You may see them in the sense that you'll be asked to draw a structure, but yeah, I'm not going to do any multiple choice structured questions. I think there's some just like, is this molecule polar? That's a multiple choice question. But yeah, I'll just do the geometry as a free response. But let's take a little 10-minute break there. So let's come back at noon.
Derived just with the compound, which is very nice. I originally thought that I had two, from the 20th of January to the 1st of February. Yeah. Because you're sending it to Idaho or something. I started to regret saying yes. I didn't even look at the dates, I was like, yeah, sure. And then I looked at the dates.
I have 14, but 12's in my office, so yeah, if you come up after, I can get it for you.
Okay. gunship. It's all, yeah, yeah. Go over there and, call for some fire from them. But I guess it's not gonna be like the whole mission. It's really all going towards like one day of it.
That makes sense.
One, two, three, four. And my buddy who was like conventional forces, whenever special forces, and I guess he's one of the lead planners, because he's stationed out on the and he texted me, he's like, "Hey, are you going to this? Because I'm planning it." And I was like, "Oh, I wasn't at first, but that's right." Hopefully, I just know next time I'm gonna be another. It's gonna be like this trip all over. Just with missing ones.
Oh, yeah. Oh, for sure.
We were playing catch up. It was a very good deal.
Yeah, super sick too. I'll call it. So I was sick during this lecture, I believe. What's the idea behind like flipping them and canceling out?
I mean, you're just trying to add it up so that right when you add up everything on the reactants and the product side, that you get whatever we were asking about.
Okay. And that's just something that you
Yeah,
can do. It's
well,
just-
you do it because, like, going back to the lab, you know, we can't do the magnesium oxygen combustion directly in the calorimeter. Like, we saw how wildly exothermic that was, right? We did it in the crucible. So it's like, okay, we can't measure this directly. How else can we find it?
Okay.
All right, let's do one more enthalpy one as we come back. Let's warm up with that. So what are we thinking for this one? Which equation do we have to flip, if any?
The first equation.
So flip the first equation, so let's do that. And then let's rewrite it now. So now xenon difluoride gives us F2 plus xenon. And now let's try to add that to our second one. So xenon plus 2, equivalence of fluorine, gives me xenon tetrafluoride. And so now trying to cancel out. So at least one fluorine cancels. Xenon cancels, so that leaves us with what we wanted. So we can rewrite it. So xenon difluoride plus one equivalent of fluorine gives us xenon tetrafluoride. Oh, and then what's the math on that one? So we said we had to flip that equation. So that would give us positive 123 plus negative 262. So what's our change in enthalpy for this one?
Negative 139.
So negative 139 kilojoules, so that sounds good. And I see that in the chat. That one was a little easier, but. Let's see, let's practice. Let's do a few just geometry structures. So see if you can draw out this bromate ion. So notice the negative charge on there. And so before you start trying to tell me what your structures look like, of course, the most important thing is total number of electrons here. So right, bromine brings 7 to the table. We have 3 oxygens, so they're bringing 6 each, so times 3. And then, of course, right, our negative charge on there, so bookkeeping, so we have to add an electron. And so is that, so we have 18 plus 8, just don't want to screw up my mental math there. So 26 total electrons in the system. And so, right, there could be a variety of resonance structures, but again, most important thing is you want to have 26 electrons in our system. And so what do we get? Just you know, again, these things don't necessarily have to be right, or it doesn't have to be the definitive structure. So what's something that we drew here? Yeah,
So I don't know if oxygen can form triple bonds, but I put bromine in the middle, and I took 3 oxygens on the outside, just because molecules like to be symmetrical. And I drew triple bonds between each oxygen, but I don't think that's correct.
yeah, so I probably wouldn't put a triple bond, but we could start with, so what if we just start with a single bond, right? Let's just start with the simplest. Fill in our electrons, right? So let's get to 26. So 1, 2, 3, 4, 5, 6, so 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So this is one structure. And then again, right, the next most important thing about your structure is your formal charges. And we know we need an overall charge of -1. And so looking at these oxygens, they're all symmetric. What's the formal charge on these oxygens here?
0.
So check that again. So remember, formal charge, so we take our number of valence electrons minus number of bonds minus electrons. So for oxygen, again, in this case, are all symmetric, so 6 minus 1 minus 6. So what does that get us for a formal charge? So -1, so write that on all your oxygens. And then if these are all -1, what do we suspect our bromine must be? / we can also do the calculation. What's our formal charge? Check it, because remember we have a -1. So other way. 2, yeah, so 2 plus. And so this is one valid structure, right? This is good. But like we kind of talked about in class, we might want to minimize this, right? We have a negative charge right next to a positive charge. And so I wouldn't go all the way to triple bonds, but I might draw some double bonds in there. Yeah, question or?
Yeah. Is it implied that the bromine is what carries the negative charge?
So from this structure, the oxygens are carrying the negative charge in all of these.
Okay.
And then actually, so right, we can kind of refine that with our resonance structure, right? Because this is not maybe ideal that bromine has a positive charge on there. And so that's where, right, the double bonds now are a little better. Again, in some arguments. So we'll have one single bond still, and then bromine still has a lone pair. So again, all I did, right, was move one of these electrons into a bonding pair, so a pair of these, and same thing, right, I moved a pair.
For the last part of the formal charge equation, are you just doing the extra electrons left over?
Yeah, so basically minus each individual electron. And we haven't looked at too many radicals, but right, that would mean like for a radical, again, each individual one. And so now comparing formal charges, so now we still have a -1 on our oxygen, but now our bromine went away, right? So 7 minus 1, 2, 3, 4, 5, 6, 7. So now we have a 0 charge there. And so again, right, our structure is telling us the negative charges on the oxygen. And then, of course, we can draw more resonance structures, just showing how that negative charge, right, can rotate around.
Can we draw a single superimposed resonance structure like in the textbook?
I'd rather you draw it out separately, just so it's more clear. And then what's a criticism of this structure, though? What's kind of a, not necessarily a problem, but we should just point it out.
It's asymmetrical.
So that's okay, right? That's where the resonance structures come into play, but there's something else that's a little,
Doesn't the
That's okay.
Bromine has 2 electrons.
Not more than 2. So how many total electrons, though, does bromine?
10.
I think it feels more than that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so, right, that's okay. So it has 12 total electrons that it feels, right, on our bromine. And so it can go hypervalent, so that is, right, a term, that's okay. And we mentioned, right, that typically happens with the third row of the periodic table. And it's more of a size argument rather than a d orbital argument. So next quarter, I'll get way too excited about MOs, and we'll talk more about that. But basically, as long as it is large enough, so we mentioned it starts on phosphorus, right, where it can be hypervalent. And we saw phosphorus with 10 electrons, right? We can see sulfur with 12 total electrons. And then, right, we'll see that with the noble gases, that they can do these expanded octets. And the halogens as well. Yeah. Except again, right, that's the erroneous part. So we're not invoking d orbitals. So d orbitals are not invoked here. But again, I'll get way too excited and talk about all that second quarter. All right, should we do another geometry, or should we do some more stoichiometry? How are we feeling?
You got a geometry question?
Okay, let's do then, let's see how we feel about IF3 then. See if we can draw out a structure for that. So how's our I of 3 looking? Do we have a structure? Yeah, well, let's start off with how many total electrons did you get in your system?
28.
So 28, that sounds good. So write 7 times 4, since they're all halogens, 28, so that's an excellent start. And so then tell me about your structure.
Iodine has 2 pairs of electrons that aren't paired.
So 2 lone pairs, and then did you just end up doing single
3
bonds?
single bonds for the fluorine, yeah.
So that sounds good to me. So just fill in all the electrons. And then no formal charges in this one, right? You can just, I wouldn't expect any just because it's neutral, but it's still always good to kind of glance at it. And so again, right, if this was a multiple choice question, I might ask how many lone pairs are on iodine.
Sorry, how many lone pairs again?
Yeah, so then write 2 lone pairs. Yeah, because remember, they're in pairs. All right, should we do a combustion analysis question or a molarity stoichiometry question?
Combustion analysis.
So let's do that then. Oh. So let's do, we'll do a tricky one. All right, so see if we can start this one. So we have some biochemical substance with carbon, hydrogen, and oxygen was burned. And then we found that we had 18.942 grams of carbon dioxide and 7.749 grams of water. So see if you can determine the empirical formula. So start walking me through this. So what do we do?
I did a molar conversion for CO2 and water.
So find moles of CO2 and water. So that sounds like a good plan. So find moles CO2. And so help me go through that. So divided by, it's 44, right?
Yeah,
Or roughly.
about, yeah, 0.43 moles.
So 18.942 divided by 44. So yeah, you said 0.43 moles roughly?
Yeah.
So 0.43. Try not to round too much, so 0.05. So moles of CO2. And then, yeah, I think people are remembering. So remember, this will also translate to 0.4305 moles of carbon. Remember from our combustions, we have CX, HY, OZ, right? Gives us some CO2 in X equivalent plus water. And so let's find moles of water next. And remember how that relates. So find moles of water. Divided by about 18 grams per mole. You guys can add more sig figs. And so we get, actually get the same number. So do we get 0.4305 moles of water as well? But then what was the trick of that one? So how did that translate to moles of hydrogen? What was the key there? Let's look back to your H2 versus so how does this translate though to moles of hydrogen?
It's the only element after the combustion that contains hydrogen. So every mole of that contains 2 atoms of hydrogen.
Perfect, right? So we got that. So right, our hydrogen becomes water, but H2O. So now, right, 2 atoms, so we could set up a proportion if that helps us to see a little clearly, right? So then we're formally saying, okay, for every 1 molecule of water, there's 2 hydrogens. So we can multiply it by 2. And, I mean, it just so happens right there, the same amount. It's okay that they're equal. And then we want to say, so times 2. So we have 0.861 moles of hydrogen anyways. And so then where do we go from here? So what do we have to calculate next?
Same thing for oxygen.
So kind of the same thing for oxygen, but what's the problem with oxygen?
It's in CO2 as well.
Yeah, so
That's
it's,
also what you get when you burn.
and we added, right, some unknown amount of oxygen.
Right.
So what do we have to do? We have to do something a little bit different. I think we were kind of saying it right because we were finding moles of carbon and hydrogen in our original sample. So what can we do?
Do we skip right to carbon?
What do you mean skip to?
You can find the molar amount of carbon, because that's not added. There's not an unknown amount of carbon being added. Never mind.
Yeah, so we got moles of carbon, right? We have moles of hydrogen. We have mass of the original sample. So what do we have to do to figure out, right? Because basically I'm trying to figure out, well, how much oxygen was in my original sample, right? Because I have moles of carbon, I have moles of hydrogen, and so I'm already gathering, right, they're in a 1:2 ratio for my formula. But I don't know my oxygen at all. So how do we get that? We forgot that last little step. We have moles.
You could do a molar conversion of the original sample. Actually, no.
Yeah, so you're on the right track, right? So we want to do that. So we want to figure out how much is in the original sample. So yes, right? But we found that in moles. So okay, we said we had 0.4305 moles of carbon in our original and 0.861 moles in our original. So let's convert that to mass, and then we'll figure out how much of this then was oxygen. So let's do that. So find mass of carbon and hydrogen in OG sample. And so now I can take my 0.4305 moles of carbon, multiply it by 12, and then we want to repeat that for hydrogen, so 0.8 moles. Multiply it by 1 hydrogen. So let's see where we're at. So 0.4305 times 12 plus this times 1 essentially. And so I get about 6 grams of everything in our original sample. So 6.0338. So that's grams of carbon and hydrogen, right? And so it said the original mass was 12.9. So now let's do that. So 12.915 minus that. So now that's mass of oxygen in our original sample. And so we just have to get moles to get it into our mole-mole ratio. So 6.88 grams of oxygen in OG. So right now convert this back to moles. So 6.88 divided by 1 atom of oxygen. And so looking good for our number wise, so 0.43, roughly. And so now we can get our mole-mole ratio. So go back and divide by the smallest. And so that would be, right, oxygen. And so right away we can see they're at a 1 to 2 to 1 ratio there. So 1 carbon to 2 hydrogens to 1 oxygen. questions on that one?
So you essentially, find the molar conversion for the ratio of products, and then add their masses and subtract that from the total reactant.
Yeah, from the total original one that you combusted, exactly. And then that left you with how much oxygen, right, was in the original sample. So 6.88, and found moles there. So yeah, the last step, right, so did you follow to at least getting 0.43 moles of oxygen? And then once you got the 0.43, we could just divide it, everything by 0.43. And then I just kind of did that in my head pretty quickly, since we kept kind of getting the same numbers. So that worked out for 1 for carbon, and then we repeat that for hydrogen. And got there 2, so that worked out very nicely for our 1 to 2 to 1 ratio there. All right, other questions on that one? So let's see, we could do another moles one, or we could do stoichiometry with molarity. Any last
The polarity one?
molarity?
I think
Oh, I said molarity, but yeah, let's do a molarity one. We haven't done that. So if we have a 0.1 molar sodium hydroxide solution, and it took 15.78 milliliters to neutralize it, to neutralize 2 mils of vinegar, which is acetic acid, or acetic acid solution. Then how concentrated? Is the vinegar. And let's try this weight per volume. And so that's just going to be in the units of grams per milliliters. So you're basically trying to calculate the mass of acetic acid is what it's asking for.
Are we going to be provided with the chemical formulas of polyions?
Oh, like acetic acid.
Nitrate and whatnot?
So you have your polyatomics. But that being said, I can give you acetic acid. So I'll try to be cognizant on the exam. So acetic acid is CH3COOH. Yeah, so you can use that for the free response. I guess you can use it for multiple choice too. I'll allow that, the polyatomics. All right, how's this one coming along? What do we need to find?
Can we set it up as a M1V1 equals M2V2?
I probably wouldn't do that just because it's asking more for like grams. So I'd probably just go for like a mole calculation. Well, that being said, I don't think you would be wrong necessarily. You just have to recognize they're in a 1-to-1 ratio, which could also throw you off if it's not a 1-to-1. So what do we need to calculate? And maybe, so I'll bring up another quiz problem that some people more people got this wrong than maybe I would have expected. And so similar sort of ideas, different questions, obviously, but right, still going with this concept of molarity. So this was from last week's quiz, right? And so you were given this equation, you had these milliliters of stuff. And so what do we need to do for this one, for the quiz? And it's basically, right, the first step of this problem too.
Need to multiply the amount of milliliters, I convert into liters by the amount of moles of the compound.
Perfect, right? So for this one, this wasn't supposed to be a hard question, but yeah, exactly like you said, right? Make sure you convert, because I think that threw some people off. I think in like the first question, people maybe got wrong. So yeah, just convert this to liters. So times 0.25, and so you should have gotten 0.0037 moles for this one. 375, right? And then all you were comparing it to was then the 10 mils, so could do that, so times 0.45, so compared to 0.0045 moles. And so, right, that's how you saw, oh, okay, this one was less, right? And made it a little easy for y'all on this one in that they were a 1-to-1 ratio, so all you had to do was see who was the lowest. And so then, right, we can start off the same way on this one, right, just finding our moles. And so again, just like we had said, convert our milliliters to liters. That'll make it easier. Times 0.1 molarity. It's now 0.001578. So moles of sodium hydroxide. And so then if we want to find this gram per milliliter that it's asking for, well, first we need to figure out moles, but how many moles? What's our mole ratio for this one? So how many equivalents of sodium hydroxide does it take to neutralize vinegar? I try to give you a hint, and then I highlighted the acidic protons. So how many acidic protons are there in vinegar? 1. So it's a 1-to-1 ratio. So we can write out our equation. So now that gives us water and sodium acetate. Double displacement reaction, so 1-to-1 ratio. So that means we have 0.001578 moles of acetic acid. So then, how do we get grams from this? So molecular weight of acetic acid, anybody have that? I can check my notes. 60.052. That sounds good. So then just at the end here, now we're out of time, so 0.001578 times 60. So that gives us a mass of 0.09 grams. And so again, I probably won't ask this necessarily on the final in this grams per weight, because I think I promised not to do that. But all we have to do is take this and divide it by our milliliters anyways. And then we can convert it to a percentage there. But like I said, I'll probably stay away from the weight per volume on your exam and just stick to molarity. But I just wanted to show you that. All right, we're probably out of time. I'll have office hours basically from now until everybody goes home, I guess. We'll probably migrate upstairs though, so if you need to make up anything, we can do that as well. So again, just meet me probably in 312. I'll be floating around. Yeah, we can all migrate there, whoever needs to come. And then do pick up your quiz 8 if you want it. I try to grab and give it to people, but I know I missed some people. And then you can make appointments with me online as well. Sorry?
I don't want to do
That one's reading.
it. Or for this.
Then I'll keep the stream going for another minute or two in case there are questions.
I just have some questions on the papers. Do you want me to go upstairs?
Yeah, I do.
What are the,
So my idea was chemical dewormers in livestock. So I pulled some papers. Some of these are based in like other countries, but they are published. Does that matter?
yeah, that's fine.
Okay. Like this one's kind of interesting. You use copper oxide to prevent nematodes and sheepy goats.
Oh, that's cool.
And then like access. Should I send you the link?
Yeah, just send me the link. I think there's a few people that I owe, so I'm gonna go through because I have to get on my other computer.
And then are we supposed to be writing on them or just uploading?
Right now, just uploading. Yeah, so we're just reading more.
I don't think I got it.
Oh, yeah. Did you turn in a quiz, Salvador?
I think I had to make it up.
Oh, I might have it in another pile then, accidentally.
And did you ever find the thing in the lab?
I don't think I did, unless you had just turned it in.
It was probably like last 2 classes ago.
Then I should have graded it.
Okay.
But yeah, if you want to chat after class, I can look again through my papers for
Okay,
it.
I'll just turn in the abstract that I typed again, if that's okay.
Yeah, but yeah, we'll see if we can find it, because it should be somewhere.
Uh,
I shouldn't have just walked away.
Just abstract work on these.
Oh, 5, so it's 5 out of 25.
Okay. Are you okay with me putting this in your Dropbox? After
Yeah.
this? Okay. I just haven't had time to write out the abstract.
No, that's cool.
So, do you know about when the wildfire is created?